So yesterday I talked about a variety of experiments that give us great confidence in the idea that gravity is geometry, or more technically, that we should really focus attention on metric theories of gravity. And I ended with this list of metric theories um, that include a set of popular ones today, motivated by things like dark energy and dark matter, that are around in a kind of beyond Einstein set of alternative theories. So what I want to do today is to focus on a particular limit of this class of metric theories of gravity, the weak field limit, or so-called post-Newtonian limit, where a lot of experiments have been performed mainly in the solar system. I will probably also, that'll cover about 2/3 of the lecture, and then in the latter third we'll begin to talk about strong field tests, notably in binary pulsars, and then leading on on Monday to dynamical tests of general relativity that really involve gravitational wave signals. So to begin, I want to kind of give just a sense of what the post-Newtonian limit is. I'm not going to display big equations or tell you how to derive post-Newtonian limits. Just give you a sense of what one is looking for when you're considering this weak field slow motion limit suitable for places like the solar system. And first, just want to begin with Newtonian gravity. So for a simple point mass moving around in a Newtonian gravitational field, you know that the action for Newtonian gravity is simply the sum of the gravitational potential 1/2 v squared. That's the Lagrangian. You integrate that between 2 points, and that's the action for the field. And the Euler-Lagrange equations for that action are just dv dt is equal to the gradient of the Newtonian potential. Okay, so that's Newtonian theory. That's the Newtonian Lagrangian. Now we all know that if you have an action, you can do certain things to it that do not change the dynamics. So for example, I could multiply the action by m, and I don't change the Euler-Lagrange equations. M is just the mass of our little test particle moving around. Also, if I add a constant to the Lagrangian, that doesn't change the dynamics either, right? So I've done nothing here. This is still Newtonian gravity, all right? Well, I could also do this. I could pull out the c squared and take that expression and multiply by, and take the square root of that. And as long as I expand to first order in this small parameter epsilon, which is of order v squared over c squared, or the potential over c squared, the expansion of this to first order in epsilon is still Newtonian gravity, right? I haven't changed anything yet. So we're still in Newtonian gravity. But that allows us to think about, gives us kind of an analogy to ask, if we were in curved space-time, what would we have to do to get the next corrections to Newtonian gravity, to get corrections that are of the next order in this small parameter, of order epsilon squared? Well, if there were no gravity, then you'd drop this term, and this would simply be proper time in special relativity. This times dt, it would just be d tau, the proper time. And in other words, in special relativity, we know that you get proper time with the Minkowski metric, if I throw that away. So this is like the Minkowski metric inserted here, and that gives us the Lagrangian. But then you remember last time when we talked about the rules for going into curved space-time were to convert the Minkowski metric to the physical metric. So now if we want to think about a geodesic in curved space-time, we take the same thing. This is just d tau. But now in curved space-time, d tau, you have to put in the real metric, not the Minkowski metric, times the 4 velocities, or dx alpha dx beta dt. So going from here to here, using this rule for going to curved space-time, I get an action that looks like this. And now, if I try to compare this with this, I see that the 0, 0 component times, this is just c squared, since dx0 is c dt. So the very leading order term gives me the 1 up there. It's just the 1 here. The spatial part of the Minkowski metric part, a to ij, it's a Kronecker delta. This is just v squared. That gives me v squared over c squared. If I want to get this, there are no velocities involved, so this must come from g00. So if I let g00 be 1 minus 2u over c squared, then I recover my Newtonian action. So these terms are of order epsilon, right? So the correction to g00 is of order epsilon. This thing that just comes from the Minkowski metric hitting 2 v's is of order epsilon. So if I want to get an action that goes to the next order, order epsilon squared, I can simply read off what I need. I need to know the metric, G00, not to order epsilon, but now I need to know it to order epsilon squared. I need to calculate the next order correction to G00 if I want to get the next terms in the equation of motion. Over here, I had this is just the Minkowski metric. So if I want to get a next order correction, I need to know Gij, the correction to the spatial part of the metric. I need to know this to order epsilon, because this factor is already order epsilon. So that'll be a correction of order epsilon squared in the equations of motion. So I need this thing to order epsilon. Now something that when we have a general metric that doesn't appear in special relativity, where the metric is diagonal, the Minkowski metric, there are also time-space components possible in the metric, multiplied by 1 power of v. Well, 1 power of v is of order epsilon to the 1/2, so that means to get corrections of order epsilon squared, I need to know G0j to order epsilon to the 3/2. And so I need to know, in order to get the first post-Newtonian corrections in the equations of motion of some particle moving in curved space-time, I need to know the time part of the metric to order epsilon squared, the time-space component to order epsilon to the 3/2, and the spatial metric to order epsilon. So you don't need to know all components of the metric to the same order of magnitude. Because of this hierarchy, each metric enters the equations of motion or contributes to the equations of motion slightly differently. And you might say, well, how can there be a 1/2 power in the metric? Well, if you think about it, this has got to be some potential, some gravitational type potential. It's got one index. What's the only thing in this problem that has one index? V, and that's of order epsilon to the 1/2. So if this is like a potential of gm over r times v, that's order epsilon to the 3/2. So this then sort of gives us an idea of what you need to do if someone hands you his favorite theory. What do you need to do to get the first post-Newtonian corrections to the metric that you can use? If you want to go to higher order, 2pn order, 3pn order, and so on, you just have to get each of these to the correspondingly higher order and go to higher and higher orders as needed for the problem you want to solve. But for most of this lecture, we're going to stick to the solar system, and we will only need the first post-Newtonian corrections to these things. We also want to deal not just with point particles moving around in some fixed background. We want to deal with real bodies. The solar system consists of Earth, the sun, planets. You might want to talk about binary systems of white dwarfs, neutron stars, and so on. These are fluid objects, so you want to think in terms of fluids and not just point masses. And so here there's a well-defined way to define the variables you need if you want to do post-Newtonian or general relativistic hydrodynamics. The first variable is called rho. It's the mass density. It's an invariant quantity. It's the mass density as measured in a local inertial frame, a local freely falling frame that is momentarily co-moving with a small element of fluid that you're examining. Of course, the element of fluid has to be large enough to contain, 10 to the 23 atoms, so it's a macroscopic size, but it should be small enough that you're not worried about inhomogeneities of the gravitational field and other things around it. This is the standard coarse graining that you do in fluid dynamics or thermodynamics. So you take your fluid element, you're in a local freely falling frame, so there's no gravity, it's special relativity, and you're momentarily co-moving, so your fluid element's at rest. You just add up the number of atoms in the fluid element, multiply by the rest mass per atom, divide by the volume of the fluid element, and that's rho. It's an invariant quantity because it's defined in a frame that is invariantly defined. Okay? So rho is an invariant quantity. It will turn out that it's very useful in post-Newtonian theory to define a slightly different density by multiplying by the root square root of minus g of the metric and multiplying by the time component of the forward velocity of your fluid element. And I'll talk about that in one moment. Another important hydrodynamic quantity is the pressure. So you put yourself in a local freely falling frame. You're momentarily at rest with respect to the fluid. You look at your fluid element and you measure the pressure, the force per unit area on the faces of your fluid element. That's the pressure. Again, it's an invariant quantity because of the way it's defined. You also look at your fluid element and you add up all the forms of other kind of energy in the element. Thermal energy, magnetic energy, anything except rest mass that comprises the energy of that fluid element. And one defines typically, you take that total energy and divide by the mass of the fluid element. So it's a dimensionless quantity. It's the internal energy per unit mass. And then finally, your fluid element is moving through space-time. And so the forward velocity of the fluid element is simply the forward velocity of your freely falling frame momentarily co-moving in space-time. So you can define, and then here you can break it out into components in some chosen coordinate system. This particular combination of the invariantly defined mass density and these variables called rho star is very nice because it satisfies a current conservation law. The underlying reason is just the conservation of baryon number. If you have some ordinary fluid element, you just added up the atoms and their rest mass per atom. Baryon number is conserved to very high precision. The proton decay rate is 10 to the whatever it is, 33 years. And so the number of atoms in your fluid elements always stays constant because the fluid element follows the atoms, and so the total number of baryons must stay constant. And as long as the mass per baryon is constant, this thing satisfies a continuity equation. And in coordinate language, it's very nice because it's like the same kind of continuity equation that you get in ordinary Newtonian Eulerian hydrodynamics. d rho dt plus div rho v is 0, but this is a fully relativistic exact expression. But again, the assumption is the conservation of baryon number. This turns out to be extremely useful in developing the machinery for doing post-Newtonian physics. Typically, in your theory of gravity, you'll have a stress energy tensor that is of the matter that is the source of the of gravity, and there's kind of a hierarchy for the components of these variables. The 0j component relative to the 0,0 component is of order v over c. Once again, the only thing with indices with a single index has to be a v. And tjk relative to t00 is of order v over c squared. Again, it's of order v squared, so you have a v squared. And also, the spatial part of the energy momentum tensor can also have a pressure term, and pressure is also relative to density is also of order epsilon. So these variables are themselves of the same post-Newtonian type order. Okay. So with this kind of hierarchy, you can then try to sit down and solve Einstein's equations and work out the next order contributions to the metric that you need for post-Newtonian theory. And I'm just going to sort of present the results. I'm not going to derive anything, and kind of illustrate the structure. So here's G00. We've already seen these first two terms. And here are the epsilon squared correction terms. Here's the term just proportional to u squared, right? So this squared is of order epsilon squared. There's a potential that is generated by other forms of energy in your fluid. So this psi is a potential, just like the Newtonian potential, but the source is the kinetic energy density and the gravitational potential energy density. So gravity itself is generating gravity. The internal energy density generates a potential. And the pressure inside the body, it also generates some gravitational potential. So there are four terms here that are produced by the kind of internal hydrodynamical variables of the body, of your material, whatever you're looking at. There's a term here that has this weird potential. It's called a superpotential. This is the name given to it by Chandrasekhar. So x minus x prime is not in the denominator as in the Newtonian potential, but it's in the numerator. But it has two time derivatives, partial time derivatives operating on it. This potential turns out to be a manifestation of the fact that gravity in general relativity does not propagate instantaneously. There's a finite speed to the gravitational interaction, and that is literally what this term comes from. It's the slow motion expansion of the retardation of the gravitational field due to the finite speed of gravity. Here, there's a vector potential in G0j, so this is kind of analogous to the vector potential of electrodynamics, but its source is the mass current, not the electric current. And then in the spatial part of the metric, the same Newtonian potential appears as the epsilon correction there. Okay, this is written in a particular gauge, so you can make coordinate transformations to make things look a little different, but this is one specific gauge that's been chosen to express this post-Newtonian metric. Now, it turns out, however, that if you look at a wide range of theories, such as scalar tensor theory, Tevez, many theories, and you derive their post-Newtonian limits using the same methods, that the answer you get looks very similar to this. The only thing that varies from one theory to another is the coefficient here might not be 2, but it might be 1.6, or it might be something that depends on some parameter that's built into your theory. So one way to kind of encompass a wide range of theories is simply to stick in here an arbitrary parameter gamma that will vary from one theory to another. In general relativity, it'll be 1, but it could be 0.2 in your favorite theory. And for example, here, you might get a different coefficient in a different theory of gravity. So one sticks in another parameter beta in front of that term, and that will depend on the theory you're looking at. And in fact, you can do this for all the terms in this sequence. You could put an arbitrary parameter here, 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 here. You can put one in front of the vector potential. You can put one in front of this superpotential term. And it turns out there are two other potentials that appear in most other theories of gravity that those can occur, so you have to add two other coefficients. And what you end up with is a framework that has 10 arbitrary parameters whose values depend on the theory that you're looking at. And this framework was first devised by Ken Nordtvedt in 1967, and then I generalized it and turned it into a hydrodynamic picture while he used point masses, and then together we kind of unified the whole thing into what's today called the parametrized post-Newtonian formalism that's both useful for analyzing theories of gravity. You look at the theory, you find out what the values of the parameters are, but also for studying experiments, because this allows you to predict the behavior of systems in terms of these parameters. And so you can make measurements, do experiments, measure the values of these things, and then ask what theory best agrees with those values of the parameters. It turns out that when you just write down these 10 parameters, you have to, if you choose them in a clever way, then different parameters mean different things. They have a heuristic meaning that really tells you something about the theory of gravity you're looking at. So for example, gamma, it appears in the spatial part of the metric. So it really tells you something about the curvature of spatial sections. So take a constant time hypersurface and ask, what's the curvature of that spatial hypersurface? That curvature is simply proportional to gamma. So it's sort of a measure of how much spatial curvature is produced by an amount of matter in your favorite theory. In general relativity, its value is 1, but in scalar tensor theories, its value depends on the value of a coupling function, and it's, as you see, it's always less than 1, because omega is always positive in these theories. So it's always slightly less than 1. This beta function says something about how nonlinear gravity is, because it depends on the square of the Newtonian potential. So in general relativity, it's 1. In scalar tensor theories, it could be 1 plus a function of the first derivative of this omega function with respect to the scalar field. There are 4 parameters that tell you whether or not your theory of gravity satisfies local position invariance and local Lorentz invariance. Now I'm going to talk about these invariances in a moment. They come under the category of the strong equivalence principle. But you can have theories of gravity in which, if your system is moving relative to some preferred rest frame of the universe, there will be observable effects that depend on that motion. If any of these parameters is 0, then a system moving through the universe will behave in a way that where you could tell there are effects due to your motion through the universe. So these are a kind of violation of Lorentz invariance in gravity itself. And there are many theories for which one or more of these parameters vanish. Yeah. If I said zero, I meant non-zero. Sorry. If anyone is non-zero, so in general relativity, there's zero, no such effects occur. A moving system behaves just as the same as a system at rest. There's no preferred frame in the universe for gravity in GR. Same in scalar tensor theory. This is no big shock because these theories take the metric and add to it a scalar field, and a scalar field is invariant under Lorentz transformations. So there's no way you can have a preferred frame in a scalar tensor theory. But in vector tensor theories, these things are typically non-zero because a vector field, if it's generated, say, by all the matter in the universe, has a preferred frame in which that vector field only has a time component. Presumably that's the rest frame of the cosmic background radiation, and since we move relative to that at 368 kilometers per second, in such theories, that motion produces effects that you can measure. And as we go along, I'll talk about experiments that have placed upper limits on these parameters. And there's a parameter here called xi and certain combinations of other parameters that where you can have preferred location effects. Local gravitational physics can depend on where you are. And one manifestation is that big G, the gravitational constant that governs us and the structure of the Earth, can vary depending on whether you're closer to a distant body or farther from a distant body. We'll see some of these effects explicitly. And finally, 4 parameters tell you whether your theory of gravity obeys a conservation law for momentum for isolated systems. You'd say that should be pretty obvious, but there are theories of gravity for which it's not true. But one statement you can make is that any metric theory of gravity that's based on an invariant Lagrangian automatically has 0 for these parameters, and that's straightforward to show. And 99.9% of modern alternative theories do begin with a Lagrangian, so they all predict 0 for these particular parameters. On the other hand, if they're non-zero, will be observable effects, and you can place upper limits on these parameters, and all the results today are consistent with 0. But they're all 0 in GR, scalar tensor theory, in fact, in any Lagrangian-based metric theory of gravity. So from one point of view, the goal then is to try to measure all these parameters as best you can and see how the values come out and what theory best matches those values. Okay, any questions? Yeah. I don't think so. I mean, partly because this is just a weak field limit. So Lagrangian is an exact theory, and this is just the limit. So and you could imagine a theory in which you contrive with some adjustable coefficients to force these to be 0 in this particular limit, yet your theory is still not based on a Lagrangian. I don't know of any examples, but I suspect you could do it. Any other questions? Okay, so let's begin with talking about some experiments, solar system experiments initially, that can measure some of these parameters. And I'll start, of course, with one of the classic tests of general relativity for historical reasons and for many other reasons. It's the famous measurement of the bending of starlight done in 1919. Einstein predicted that light would be bent by the sun, and in the closing months of the First World War, Arthur Stanley Eddington and put together 2 teams of astronomers to try to measure the bending of light during a total eclipse of the sun. The eclipse was May 29, 1919. By then the First World War was over, so they traveled to Principe, which is an island off the coast of West Africa, and the other team went to Sobral, a city in northern Brazil, along the path of totality of that eclipse. And the idea is that you, during a total solar eclipse, the moon blocks the sun, and you can actually see stars near the sun. This is one of the photographic plates from Eddington's expedition, and you can see the little dots here. You can't distinguish them from dirt on the view graph, but I assure you that they're there. And God puts in the little tick marks to help guide your eyes so you can find them. But in fact, there are stars. You can see stars during the eclipse. The idea then is to first, 6 months beforehand, take a photograph of the same field of stars when the sun is not in that part of the sky. That establishes the nominal positions of all the stars. Then, during the eclipse, you take a photograph of the same field with the sun in here. Because light is bent from this star, the star's position will appear to be shifted away from the sun because of the bending. And the bending is inversely proportional to the angular distance from the sun. Of course, it's weaker way out here, stronger for rays that really go close to the sun. So stars out here won't be deflected by much. Stars here will be deflected more, inversely proportional to the distance. And then you compare the earlier plates with these, measure all the deflections, and you measure the deflection of light. In November 1919, after the 6 months of analyzing the data, Eddington reported to the Royal Society of London at their winter meeting that he had measured successfully the bending of starlight, and it agreed with Einstein's theory. And this caused an overnight sensation. Headlines around the world proclaimed this new world. This is the New York Times the next day. Lights all askew in the heavens. Men of science, notice only men of science, right, no women, of course, more or less agog over the results. Not completely agog, just more or less agog. Einstein's theory triumphs. Stars not where they seem, but don't worry, etc. So that you can get the hyper publicity that was generated, some of it actually engineered by Eddington himself. He was a master publicizer of himself, actually. But nevertheless, there were a lot of doubts about the measurements. They were not terribly accurate. In fact, many astronomers, especially American astronomers, were very dubious about Eddington's measurements. Ironically, Campbell and Curtis from the Lick Observatory in California had examined photographic plates from a 1918 eclipse over the state of Washington, and they reported at the summer meeting before Eddington's big announcement, but at the summer meeting, they reported that they had not been able to measure the deflection. They got no deflection in their measurements. At that meeting, rumors were already going around that Eddington would be reporting a positive result, but the Curtis Campbell team reported no result. So it wasn't completely clear, from a historical point of view, it was not exactly a slam dunk. Nevertheless, these reports in the newspapers made Einstein an instant overnight celebrity. I mean, literally overnight, he was proclaimed around the world as the next Newton, genius, blah, 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 blah. So, no more in all the world could comprehend it, said Einstein, and so on. And from that moment on, Einstein was a famous person. Well, so this is sort of nice history, but let's be a little more quantitative about what the measurements mean. Yep. I mean, there's been a lot of dispute and debate about it. It was, and I'll show the actual error bars in the next slide. It was sort of 10 to 15%. Some people thought he kind of underestimated the systematic errors in the measurements. You need a lot of stars to get a credible measurement, because the effect of seeing, the bending of light just due to atmospheric turbulence, is more than the deflection you want to measure. You want to measure a deflection of at most 1.75 arc seconds. That's the deflection of a ray that just skims the surface of the sun, but typically you're 2 to 5 solar radii away, so you're measuring maybe 1 or half an arc second of deflection. But the deflection of light just due to atmospheric turbulence is a few arc seconds. So you need lots of stars so that you can average those random fluctuations and see the net displacement of the stellar images from the sun. Well, in Eddington's case, the morning of the eclipse, there was a huge rainstorm, and the clouds only began to clear as totality approached, and so we only saw about 6 stars. So not good statistics in terms of averaging away all these larger effects. But later people have looked at Eddington's data, especially after some philosophers of science showed that he charged that he had selected data. He had rejected data from one of the Sobral telescopes because it didn't agree with Einstein's theory. So they made some rather strong accusations about that he may have manipulated data because he really loved general relativity. But most modern observers, even some who have reanalyzed his original plates, have concluded that the results he got were actually very credible. And there was no evidence that he had any kind of bias in his data. But let's kind of describe quantitatively this, and then illustrate the history of the measurements of the deflection of light over time. Well, what does this measurement actually measure? Well, it measures this parameter gamma. The bending of light has a factor in front of it, 1.75 arc seconds as the maximum, but it's multiplied by this factor 1 plus gamma over 2. Now, why is it 1 plus gamma over 2? Well, the 1 over 2, the half, is the bending that you would get if you simply took Newtonian theory and asked what's the bending of a hyperbolic orbit around the sun in the limit when the speed of that particle tends to the speed of light. It's elementary calculation, any undergraduate can do it, and what you get is half of the bending. The other half, the gamma over 2, comes from the fact that straight lines, as defined by rigid rulers, stretched across the sun, close to the sun, are themselves bent due to space-time curvature relative to the same kinds of rulers stretched across the sun but far from the sun, where space-time is a little flat. So the total bending is the Newtonian bending relative to straight lines that are themselves a little bent relative to straight lines far away. So it's really a sum of two effects, and only this part depends on the theory of gravity you're looking at. So here I've plotted then as a function of year, 1920 to the present, and just look at the top half for the moment. There's the general relativistic prediction, 1 for this coefficient, and this dot and its error bar and that arrow that's somewhere up on the floor above us are the results of the two Eddington expeditions, one the Africa team and the other the team in Brazil. I think this is the one from Brazil. It's way up there somewhere. So they certainly were consistent with general relativity. They were inconsistent with the Newtonian bending, which would just be half, which is somewhere down on the floor below us. So Newton was clearly wrong. But, you know, there was some, it wasn't exactly a slam dunk for Einstein's theory. So it became important to repeat these experiments, mainly during solar eclipses, and during the 20s, 30s, and 40s, many experiments were done. And again, it wasn't conclusive. Some experiments were between 1.5 and 2 times the Einstein prediction. Some were fairly close to the Einstein prediction. This one measurement, I want to say a few words about because this it brings us back to Les Ouches, in fact. There was a total eclipse of the sun that was passing over Mauritania in Western Saharan Africa in 1973. And a team from Texas and Princeton University, the Texas team headed by Bryce DeWitt, one of the founders of Les Ouches, and Richard Matzner, whom many of you know, and some astronomers from Princeton set out to repeat the Eddington measurement, but using 1970s era telescopes. They had telescopes, they had Kodak emulsions, not the plates that they used in those early days. They had a computer-driven mounts for the telescopes to keep them going. But in the summer of 1972, during the Les Ouches school where I was a student, they had gone a year earlier to take the photographs of the stars without the sun in the sky and to scout the location for the actual eclipse part. And one evening at that Les Ouches summer school, Bryce DeWitt gave us a slideshow of their expedition scouting the place in this desert to do the measurements. And he showed great pictures of Bryce and Richard Matzner with, the Arab type garb, riding camels across the desert, I mean, like Bedouins. So it was a great slideshow showing their preparations for this measurement. At the end of the day, they didn't do any better than Eddington, largely because there was a huge dust storm. They expected to see about 150 stars around the sun. It was a very rich star field for that particular eclipse. But because of the obscuration due to the dust, they only saw about 20% of what they expected. So again, they had large error bars, not much better than Eddington. I'll say a few more about optical measurements, but then I want to return to what's really the modern way of measuring the deflection of light. Of course, there was a space astrometry mission called Hipparcos that measured angles to millions of stars with milli-arc-second accuracy. They produced results at a fraction of a percent. This was a very interesting measurement using galactic lensing, and it's been actually updated since then. The idea is to measure the gravitational potential of a series of galaxies. This is done using data from the Sloan Digital Sky Survey on elliptical galaxies, about 20 elliptical galaxies. You can measure the lensing by the galaxies, but if you want to test GR, you also have to know the gravitational potential that's doing the lensing. So they get the gravitational potential by building a model that's consistent with the dark matter halo around the galaxy, and then using that to calculate a potential, use that to calculate the lensing, and compare that with the measured lensing. Again, the accuracy wasn't great, but this is the bending of light on galactic scales, not just the bending of light by the sun. And then the final one I want to mention is kind of cute. During the American eclipse of 2017, across western and central Midwest America all the way to the East Coast, an amateur astronomer named Donald Bruns, who's he's a professional in the optics industry, but he's a very accomplished amateur astronomer, set up a telescope in Wyoming. Now this is a very fancy high-end telescope with CCD cameras, very fancy computer mounts, lots of software to control everything. He also didn't have to take pictures of the sky without the sun there because he could rely on Gaia, the current astrometry satellite that establishes star positions to much better accuracy than you need to do the experiment. So, but he achieved a result in the end that was about 3 times better than Eddington's measurement in 1919. So I think thought it was cool that this one guy, there he is with his telescope, managed to beat Eddington by a factor of 3. But he had all the modern tools at his disposal, and he had fantastic weather. I mean, it was sunny and clear the whole time of the eclipse at that site in Wyoming. In fact, it was pretty good all across the country, except maybe in Illinois where there was rain. But of course, the real revolution in measuring the deflection of light came with radio astronomy. Starting in the 1960s, people began to measure the angle between quasars as they passed close to the sun. So for example, every October, 3C273 and 3C279 pass close to the sun, one very close, so that the light from radio waves from one quasar are bent more than from the other, so the angle between the two quasars varies as the pair pass by the sun. And these could be measured with radio telescopes, radio interferometry, and between the late 60s and mid 70s, these dots just represent many measurements by astronomers, culminating in maybe a 1% measurement. And then in more recent years, using very long baseline interferometry, really high precision has been achieved. And that comes about by making huge numbers of measurements to many sources. So this is an early analysis. Again, it's been improved and updated, but just to illustrate, these are measurements of the positions of 541 quasars, 20 years of data, 87 very long baseline interferometry sites, over 1.7 million measurements. And what's plotted here is the deflection angle. So here it's a few milliarc seconds. And here's a histogram of the angle where the sources were relative to the sun. So the bulk of the sources measured were between 60 and 120 degrees from the sun. In other words, a light ray that just grazes the surface of the sun is bent by 1.75 arc seconds. A light ray that comes 90 degrees from the sun is bent by 4 milliarc seconds. But modern VLBI operates at hundreds of micro arc seconds. So 4 milliarc seconds can be measured quite easily. Even a ray that comes in at 175 degrees from the sun, almost in the complete backward direction, is bent by just under a milliarc second. So with these kinds of modern techniques, lots of measurements to build up statistics, then one can measure the deflection of light very precisely. And so the latest analysis is at the part in 10 to the 4 level on this coefficient. Okay, any questions about light bending? Yeah. Oh, but I haven't shown the error bars. In most cases, in all but one case, the error bars are consistent. But it would just, if I put in all the error bars, it would just be a mess. I just try to give a sense that there are a lot of measurements. Okay, there's actually another way to measure this same coefficient having to do with how light propagates, and this is the Shapiro time delay. When light passes by a massive body like the sun, and say on a round trip from Earth to a spacecraft and back, there's an excess delay for the sun for a ray that grazes the sun, it's on the order of hundreds of microseconds. Um, that was first calculated by Irwin Shapiro, a famous radio astronomer, and then measured by him by bouncing radar signals off Venus. The early measurements, of course, weren't very accurate, but over time they got better and better, and the best result to date comes from the measuring the time delay of tracking radar signals to the Cassini spacecraft. We all think of Cassini as exploring Saturn and sending down the Huygens probe, and it was all great planetary science. But on its way to Saturn, Cassini was on the far side of the sun, about 8 astronomical units away, but the tracking signal went within 8 solar radii of the sun. So you got a very huge effect, about as large as it could be, and Cassini had the advantage of X-band and K-band radar. So with multiple high-frequency radar, you could reduce the effect of the solar corona, which also adds its own delay to the signal. So they measured the same coefficient to an accuracy of about a part in 10 to the 5. So that currently is the best measurement of gamma today from the Cassini. Yeah. It's not Cassini, it's called the Pioneer anomaly and Voyager. Yeah. I'll say it very quickly. I want to move, and maybe if there's time I can mention it, but the general agreement now is this was an anomalous acceleration of the Pioneer spacecraft that seemed to be constant and directed away from the Earth. Didn't depend on distance from the Earth. But now it is generally accepted that this was anisotropic radiation of thermal radiation from the spacecraft, because it contained these RTGs, radiothermal generators, basically sources, I think, of plutonium that generated electricity and heat. But the spacecraft radiates the heat anisotropically, because the spacecraft is something, it has solar panels, all kinds of crap around it, and it's that anisotropic radiation that produced the acceleration. And that's the consensus view these days. No new physics, although there are 1,000 papers written about it, right, saying new physics. At the end of the day, it was just mundane spacecraft engineering. Not that spacecraft engineering is mundane, but it was a sort of a boring yet satisfying conclusion to the anomaly. And of course, we all know about gravitational lensing. This is I call it Einstein's gift to astronomy. Bending of light that produces gravitational lenses, now used for everything from hunting for dark matter to searching for exoplanets. So, so gravitational lensing is great. Gravitational lensing has also gone to Hollywood and produced an Oscar. This is from the Interstellar, the motion picture Interstellar, directed by Christopher Nolan. Executive producer was Kip Thorne, who worked with Nolan on all the scientific aspects. And this is an image of the supermassive black hole Gargantua from that movie. And there were supposed to be planets orbiting it where we're supposed to be looking for a new place for mankind because Earth was dying. Now, why the hell you would ever go near a black hole? I'd rather stay on Earth than tough it out, right? But this was the movie. But this is an image of as they approach the black hole. This is what they were seeing, and what you're seeing here is the accretion disk around the black hole. But you might ask, what's this? This is the top side of the accretion disk behind the black hole. Light is coming off that disk and bending toward your eye by 90 degrees. It's a strong gravitational lensing due to the black hole. And this part is the underside of the disk behind the black hole. The light is coming out and then being bent by 90 degrees to see you. And what's interesting about this thing is that Kip and the special effects team in London, Double Negative, this is a real calculation using ray tracing software in the exact Kerr geometry with the mass and spin that Christopher Nolan wanted for the black hole. He had special criteria that he wanted it to do, and Kip worked it out in detail. In fact, there's so much scientific detail in these calculations that Classical and Quantum Gravity published a paper on the calculations of these images. So, and Double Negative won an Oscar for their special effects work on the movie. Of course, wait. The most important thing about this image is that since I was a PhD student of Kip Thorne, this puts me at 1 degree of separation from Anne Hathaway and Jessica Chastain. Just saying. Yeah.
There is a book about the movie, and they discussed that actually there is a fact that they are taking out just for artistic
Yeah, yeah. That's right. So Kip wrote a book on the science of interstellar and pointed out just because of it would have been too complicated. So this does not show all the blue shift and redshift effects. They had to eliminate that just for for reasons of not making the movie too complicated and maybe cost. Who knows what criteria go into these things. All right. Another important aspect of gravitational lensing, and this is really is a bit of the strong field aspect of testing general relativity, is about to be realized with the Event Horizon Telescope. So this is a project that has brought together an array of radio telescopes around the world working at millimeter wavelengths, including South Pole, Chile, Hawaii, Western US, Europe, linking them together to produce a huge, very long baseline interferometer capable of angular resolution on the scale of the event horizon of Sagittarius A star, the black hole at the center of our galaxy, and also of the black hole in M87. Okay, so they will be able to image what's going on near those two black holes with an angular resolution comparable to the size of the event horizon of both black holes. This, of course, is our closest supermassive black hole. So that's great. You might say, why M87? It's about 1,000 times further away, but it's also 1,000 times more massive. So the angular size of the event horizon is the same, so it will be able to also image that one. And so one of the goals, for example, is to learn about matter around that black hole, explore the strong field regime around the black hole. But another is to test general relativity. People on this collaboration have looked at various ways, for example, to modify the Kerr metric with some small parameter and ask what would the image of the photons that are orbiting in, near and around the black hole look like if you had kind of modified Kerr geometries that you might conceivably get in some alternative theory. And so they have worked out some ways that you might be able to distinguish one model of the black hole from another using the imagery that they'll be able to see with this array. So this is kind of another beginnings of a strong field way of testing general relativity once this thing really gets up to its design sensitivity. So these are photons. This is basically photons at the photon ring at 3M. And of course, it's asymmetric because this is a rotating black hole, so you get all the frame dragging effects that change the distribution. Yep. So they can resolve an angle, and they can resolve angular features at the scale of 2m or m, at the scale of whatever that mass is at that distance. So we're not talking about, I mean, it's not literally horizon, but it's just an angular scale corresponding to, roughly speaking, the mass of the black hole divided by the distance to the black hole. So that's okay. For the next, of course, yeah.
That three images there, it's from different theories?
No, it's a model of a modified Kerr black hole with it's a parameter that measures how strong the quadrupole moment of the Kerr black hole is. We know it's fixed in general relativity. It's fixed by the angular momentum. So you put a small parameter in front of those quadrupole terms and let it vary, and then you get slightly different distortions of the photon sphere around the black hole. So it's just one example to illustrate the potential. That's all. Yep.
Do I remember the statuses? They've been processing data for many years, and they're going to release them in another year.
I don't know the exact status of the project. I'm not a member of the project, so I don't know where. I know they've. It's a question of getting all the telescopes on board and so on. So it's an evolving project, just because it involves so many different telescopes, getting telescope time and analyzing data. So I don't know what their specific timelines are. Okay. The next, of course, very famous. Yeah. I'm sorry? No, I think this is just, photons are orbiting the black hole. At this photon orbit, there are photons in unstable circular orbits all the time because there's light coming in from, there is a weak accretion disk around the Sag A star. It's very, very diffuse and weak. So there's all kinds of photons, and they sort of tend to accumulate and whirl around the black hole. And this is the image that you get when some of them start to escape. Okay, moving on to Mercury. Mercury's perihelion advance. This is, of course, again, a historical story as well as has a modern component. The story really begins in 1859, actually, with Urbain Le Verrier, who had a big problem. He noticed that there was he was a big expert in solar system dynamics, had worked out the orbits of the planets, understood them using Newtonian theory. In fact, his fame really was established when he pointed out that certain anomalies in the orbit of Uranus could be explained if there were another planet outside Uranus. And his calculations were so exact that he could predict roughly where Uranus, this new planet, had to be. And when he sent out the information, within a few weeks, astronomers in Berlin looked in that part of the sky and found a planet that we now call Neptune. But Leverrier also had another problem, because he was also examining the orbit of Mercury. Mercury would ordinarily orbit in an ellipse around the Sun with a fixed orientation of the ellipse, but by 1859 it was already known that that ellipse was rotating, precessing at 575 arcseconds per century. But Leverrier said, we can explain this. We know how to calculate the perturbations due to all the other planets, and so he worked out the perturbation due to Venus, Earth, Mars, Jupiter, Saturn. He worked it all out, but when he added it all up, it was short of the observed amount by about 43 arcseconds per century. And here I'm using the modern values. His values were a bit different. Well, he had an immediate answer, and many other people at that time had an answer. If we put a planet outside Uranus, Neptune, to explain some anomalies, let's explain this anomaly by putting a planet between Mercury and the Sun, and that you could pick an orbit and a mass of the planet, and you could account for the 43 arcseconds. They even gave the planet a name. It was called Vulcan, after the Roman god of fire, because it would have to be extremely hot, being so close. Actually, I believe this is the first example in history of physicists giving a really, really cool name to something about which they knew absolutely nothing. The modern example, of course, of that is dark energy. But 50 years of astronomers working to find Vulcan yielded many, many sightings, but none was ever confirmed. So by the turn of the 20th century, this was one of the big crises in dynamics. There was no explanation for this anomaly in Mercury. No planet had ever been found, and it was a problem for dynamics. Einstein was well aware of this problem, and in fact, there's kind of a legend that in his 1915 paper, he sort of solved the problem. But actually, modern historians looking at his notes realize that's not exactly true. He knew this problem well enough that he used it to filter some of his earlier attempts at a relativistic theory of gravity. So for example, in 1912, he produced what was called the Entwurf theory, a draft theory with Marcel Grossmann. He wasn't very happy with the theory theoretically, but what made him really reject that version of the theory was that it gave the wrong perihelion advance. So he already was using the perihelion anomaly as a way to test his early draft theories. But in 1915, in November of 1915, he felt he had a version of the theory that he was at least happy with theoretically. It satisfied all his aesthetic criteria. But when he, just days before the final lecture he was supposed to give on this theory, calculated what it predicted for the perihelion advance, he found that it gave the 43 arcseconds. He later wrote to the friend that when he got this result, he was so excited he thought he was having a heart attack. He said he had palpitations of the heart because of the excitement. Well, of course, the modern value of these numbers is shown here. So the modern measured value of the discrepancy, we know all these numbers much, much better because we know masses of planets better, the big computer codes to calculate their orbits, and so on. So the modern measured value is this, 42.98 plus or minus 0.002. I've just left off the digit there, but it's known to about 5 parts in 10 to the 5. And the prediction of general relativity is in exact agreement with the observation. Yep. there a question? Well, I'll get to, that's my next slide. I mean, I'm going to mention that next. So again, just to make this a little more quantitative, the prediction in this PPN framework involves both gamma and beta together. So this is the overall factor. It's 1 in general relativity, and then there are the things: mass of the sun, semi-major axis of Mercury and its eccentricity. This is the perturbation due to a third body, at least to the leading quadrupole order, and you can refine those calculations, and you just add up over all the bodies. That's more or less what Leverrier did. But there are other effects on Mercury's orbit that you might want to worry about. And this is kind of a table giving, relative to the GR prediction, a variety of other effects. So first of all is the solar oblateness. We know the sun is not spherically symmetric. It rotates, so it's centrifugally flattened. That deviation from spherical symmetry and then the extra 1 over r cubed potential produces its own contribution to the perihelion advance, proportional to this dimensionless quadrupole moment of the sun. But this quadrupole moment is now known to be about 2 parts in 10 to the 7 to about 10% through helioseismology. Measuring the normal modes of oscillations oscillation of the sun gives information on the internal rotation state of the sun. So we now know that the sun rotates roughly uniformly at its observed surface angular velocity. There's no enormous differential rotation or no rapidly rotating core. And so from those kinds of solar models, you can build an estimate for J2. And with those estimates from helioseismology, the value relative to GR is about this. And even the measurements of the perihelion shift have to take this into account. Because remember, I talked about being 5 parts in 10 to the 5. Well, this is about a factor of 10 larger. So the quadrupole moment of the sun does contribute in a measurable way to the perihelion advance of Mercury, but because of helioseismology, we know what that prediction is. There's the possibility of frame dragging due to the rotation of the sun. Estimate the angular momentum of the sun, you get this. It's down by just below the current measurable accuracy, so in the future it might be measurable. But then just recently I noticed that the potential for some other contributions to Mercury's perihelion advance that come from the fact that these other planets perturb Mercury's motion just by their Newtonian gravitational attraction. However, the sun curves space-time all the way through the solar system. And that curvature of space-time modifies the field that each planet exerts on Mercury. Similarly, each planet curves space-time around it all throughout the solar system, and that curvature modifies the interaction between the moon, between Mercury and the sun. Those effects together produce an effect that is relativistic. You notice there's 1 over c squared, but it also depends on the mass of each of the other planets. So it's kind of a cross term between post-Newtonian effect and a Newtonian third body effect. And it's at the level of a few parts in a million. And there's also a term caused by the fact that each planet moves. So it produces a vector potential. You remember we had the vector potential in our post-Newtonian limit. So that vector potential acts like a vector potential in electrodynamics. There's a V cross B effect, and that effect, because of the motion of Mercury, produces a small effect as well at the level of parts per million. There's an effect at second post-Newtonian order. This would be order epsilon to the 4th, and this is probably too small to ever be measured. But the reason these terms are interesting at a part per million is that late this year, there'll be a launch of a mission called Bepi-Colombo, which will mainly an exploration of Mercury, but it will launch 2 orbiters around Mercury. And by tracking those orbits, the orbits of those 2 orbiters, one will learn much more about Mercury's own orbit, improving the precision of that, and they claim they will be measuring the perihelion advance at the levels of a part per million. So at that point then, one can begin to be sensitive to these kinds of additional effects due to general relativity. Okay, any questions? When I want to talk about this, I've mentioned it a bit before, this strong equivalence principle. It can be stated very much in parallel to the Einstein equivalence principle that we had before, where we talked about test bodies, but now we talk about all bodies fall with the same acceleration. So a ball of aluminum and the Earth or a neutron star fall with the same acceleration in an external gravitational field. So it doesn't matter how much internal gravity a body has, if this principle is valid, it will fall with the same acceleration as any other body. In a local freely falling frame, say surrounding the Earth or surrounding some apparatus, all of physics is independent of the frame's velocity. Not just non-gravitational physics, measurements of the fine structure constant, but all physics, for example, measurement of the Cavendish, big G, using a Cavendish experiment, or just studying the structure of the Earth in the field of other planets or moving through the universe. Even experiments that themselves involve gravity, as long as you can do them in some sort of local freely falling frame, do not depend on the velocity of the frame. And the third piece, do not depend on where that frame is. So this is a much stronger principle than the earlier one that I talked about. That one established metric theories of gravity. But this one is so strong that it is known to be satisfied by general relativity, but it's violated by essentially every other metric theory that I've ever looked at in this context. It seems to be something unique about Einstein's theory that obeys this principle. The bottom line is that Einstein's theory has only one gravitational field, the metric itself. Other theories tend to introduce other fields, vector, scalar, tensor fields, and when you introduce those extra fields, they have a tendency to violate these principles. Scalar tensor theory violates the strong equivalence principle. Okay. So I'll just say a few words about some consequences of these violations and just mention some of the effects. So for example, if this principle is violated, then two bodies with different amounts of internal gravitational energy would fall with a different acceleration. And it turns out that the Utvash parameter, remember the difference in acceleration between two bodies over the average acceleration, in post-Newtonian theory depends on a parameter called the Nordtvedt parameter in Ken Nordtvedt's honor, which is a combination of parameters that you've seen, times the difference in the internal gravitational binding energy between the two bodies that you're looking at. So these S's are called sensitivities. Roughly speaking, they're the gravitational energy per unit mass, or they represent how the mass might change if you vary some external field, like a scalar field or a vector field in your theory. Notice that this parameter vanishes in general relativity. Beta and gamma are 1, all those parameters are 0, so there's no such effect in general relativity. And here are values of these factors for various bodies for the Earth and the Moon, parts in 10 to the 10, Sun, white dwarf, parts in 10 to the 4. Neutron stars, of course, are large. They have a huge amount of internal binding energy due to gravity. And in the solar system, this is tested by lunar laser ranging. You send laser beams to bounce off these corner reflectors that were placed on the moon by Apollo astronauts. These are just a flat plate with a cone made of a certain kind of glass, like the cone you get for drinking water. It's a cone, but the angle of the cone is 90 degrees, so that when a light ray enters the cone, it's reflected off one face, goes across, hits the other face, and is reflected back in the same direction from which it came automatically. So you send a laser beam take a high power laser, pass it through a telescope, send it toward the moon, it bounces off this thing, it comes back, and if it's like a pulse laser, you can measure the round trip travel time of the laser signal and measure the distance between the telescope and the moon. If there's a violation of this equivalence principle, then that would cause a perturbation in the Earth-Moon distance at the level of tens of meters times this Nordtvedt parameter, and it has a particular time dependence that you can search for in measuring the Earth-Moon distance. Lunar laser ranging began within months after the first Neil Armstrong put the first of these reflectors on the moon, and has been going on ever since. And to date, there's no evidence whatsoever for this Nordtvedt effect. So in terms of Utvash parameter, the Earth and the moon fall with the same acceleration to 10 to the minus 13. The difference in the sensitivity factor is 10 to the minus 10, so the limit you get on the Nordtvedt parameter is a few times 10 to the minus 4. So here then is a verification of the strong equivalence principle with lunar laser ranging. But there are many, many other effects that you can get if you violate the strong equivalence principle. For example, if you do a calculation of what you would get if you measure did a Cavendish experiment to measure the gravitational force between two bodies of mass m1, m2 at a distance r, the factor must be is big G. If you make a measurement of big G in a laboratory that is nearby some massive body at a distance r and that's moving through the universe with some speed, you'll see that G is not 1, but in fact could depend on the gravitational potential of the body, could depend on the velocity. It could even be anisotropic. The value you get for big G could depend on whether you're measuring the force between your bodies this way versus that way. So G isn't even the same in all directions. So you can work out the fact that if this is true, you will get anomalous tides of the solid Earth, variations in the rotation rate of the Earth. If you look at orbital effects of these kinds of, if any of these parameters is non-zero, you can get forced eccentricity of orbits that have a specific eccentricity, precession of orbital planes of binary system orbits. Spinning pulsars can have their spin axes precess, and spinning bodies can even self-accelerate in a specific way. And there have been many, many experiments that have set very tight upper limits on parameters like alpha 2, alpha 1, alpha 3, Xi, and so on. And I'll summarize those values in a moment. Somebody yesterday asked about big G as a function of time. So again, if there's local position invariance is violated, then G might vary with time as the universe evolves. If your theory has some field that couples to gravity that's evolving as the universe evolves. But there are very tight bounds on such variations. In units of 10 to the minus 13 per year, then from looking at the orbit of Mars, there are limits of order unity times 10 to the minus 13. Lunar laser ranging has set some limits. Binary and millisecond pulsars. Helioseismology, just the structure of the sun over billions of years, shows that G can't be changing by much. And Big Bang nucleosynthesis also gives a bound on G dot over G. So given that the Hubble timescale is 10 to the 10 years, this is a very small fraction of the Hubble rate of expansion. So it suggests that G is very close to being constant. So here I'm just summarizing the current values of all of these 10, or most of these 10 ppn parameters. So I've already talked about gamma from Cassini and VLBI, beta from the perihelion advance. There's some fantastic bounds on some of these weird parameters that involve violations of the strong equivalence principle. So all of these limits, of course, are consistent with general relativity. And so take your favorite theory, compare with this table, and you can ask whether or not you agree with the observations. If you are a devotee of scalar tensor theories, this puts a lower bound on the coupling parameter of those theories of about 40,000, coming from the Cassini bound on the deflection of light, on the Shapiro delay. Okay? Any comments? Another class of experiments has been done, two rather ambitious ones, to look for and measure the dragging of inertial frames, the frame dragging effect. This effect turns out to be very important in astrophysics. It's probably responsible for the jets in quasars. It's the frame dragging around a rotating supermassive black hole combined with the thick accretion around the black hole can produce forces that can cause jets to be ejected. This is the so-called Blanford's-Nyack model. Frame dragging with spinning black holes in spiraling binary orbits, of course, is a very important effect. It causes the spins and the orbital planes to precess, modulating the gravitational wave signal. And in some cases, in extreme spin cases with misaligned spins, can produce a huge recoil of the final black hole that's produced. So frame dragging due to a spinning body is a very important phenomenon in astrophysics. And so 2 experiments were done over time to try to measure this in a solar system context. I just want to say a few words about them. The first is Gravity Probe B. The idea of Gravity Probe B was to launch into orbit around the Earth an array of gyroscopes and to measure the precession of the spin of those gyroscopes due to 2 effects. One is a precession that stays within the orbital plane, and it's called the geodetic effect. And this is simply a precession caused by the fact that in curved space-time, if you parallel transport a vector, you tend to come around pointing in a slightly different direction. Okay, it's a manifestation of curved space-time, and it's a well-known effect. And it's, for the Earth, its magnitude is about 6.6 arc seconds per year. But the important effect that they wanted to measure is the frame dragging due to the rotation of the Earth. It's much smaller. It's only 42 milliarc seconds per year, but it's in a direction perpendicular to the orbital plane. And here, for various operational reasons, the orbit is a polar orbit. So it goes over the poles of the Earth. And one tries to measure any change in the direction of the spin of the gyroscope relative to some distant star that is constantly being monitored by a telescope that is on board the spacecraft. The mission was launched in 2004. It was a 16-month mission ending in 2005, and the final result was announced in 2011. Here's what each gyroscope looked like. It was a sphere of fused silica with a thin layer of niobium coating it. Each sphere was machined and fabricated to be homogeneous and spherical to parts in 10 million. That was necessary so that ordinary interactions of gravity would not induce torques on these gyroscopes and cause them to precess. The experiment was done at liquid helium temperatures because if you take a spinning superconductor, niobium is a superconductor at liquid helium temperatures, such a spinning superconductor develops a magnetic moment parallel to its spin axis. So this is called the London moment. It's a well-known phenomenon in superconductivity. And so you have this spinning sphere, which is otherwise featureless. You ask yourself, how do you tell if its spin is changing if it's a perfectly spherical object with no features on it? You might say, well, why don't you put a dot of paint on the North Pole? The trouble is that the gravitational attraction between that dot of paint and other parts of the spacecraft would cause such a huge torque that it would be much, much larger than the tiny effect you want to measure. Instead, the rotating superconductor develops this magnetic moment. You then surround the superconductor by a superconducting loop, and you can measure the change in flux through that loop as the axis of the magnetic field changes direction, right? There's a flux around the loop due to the magnetic field. If that changes due to a precession, that can be measured with fancy squid devices and all the delicate techniques of superconductivity. I talk as if I actually know all the details of this experiment. I mean, I'm a theorist, not an experimentalist, but for 13 years I chaired an advisory committee for NASA that oversaw aspects of this experiment. So I learned way more than I ever expected to learn about this kind of experimental stuff. But at the end of the day, there were some anomalies that I'm not going to talk about just for purposes of time. But at the end of the day, they did measure both effects. There are 4 gyroscopes, in each one for the geodetic effect. You notice this is like 3,000 to minus 1,000 milliarc seconds, so they could really measure the precession, this larger geodetic precession, rather easily. The smaller effect was much more difficult to measure. There were some anomalies that they had to work out, some modeling that had to be done, lots of noise, but at the end of the day, they reported a measurement of both, and particularly for the frame dragging, it was about a 20% measurement in agreement with the prediction of general relativity. Yeah.
Why did it took so long to have these results?
Mainly because of some anomalies that they discovered, mainly after the science part of the mission was over. They did some drastic changes of the orientation of the spacecraft to see what would happen, and what happened was much worse than they expected. You don't want to do these drastic things before the experiment in case something crashes into something else. So afterwards, so it turns out there were anomalous torques that they hadn't that they thought would be small but were much larger than expected. So it was a very complicated analysis to model out these torques and to get the final result. They had hoped for a 1% measurement, but instead got a 20% measurement, and it was a result of these anomalies that had to be dealt with. So they didn't do as well as they had hoped, but they did get a credible result. And it took a long time to do the data analysis. There's another way of measuring the frame dragging of the Earth, and that's by looking at a pair of satellites called LAGEOS. These satellites are really were put in around the Earth for the purposes of geodesy. Geophysicists wanted to use them, but these are satellites that are about this big in diameter. They're solid mass, so they're extremely heavy. The idea is then to reduce the effects of atmospheric drag, and they're studded with these same corner reflectors that are used in lunar laser ranging. So they simply orbit the Earth. There are no moving parts, no solar panels. They're just spheres, so they move on almost pure gravitational orbits with very few perturbations, and you can measure the distance between the Earth and these things with millimeter accuracy because laser ranging is so precise. Now, according to general relativity, if these orbital planes are inclined relative to the spin of the Earth, the orbital planes will rotate in the same sense as the Earth. That's the dragging of inertial frames. And the amount for these particular satellites is about 31 milliarcseconds per year. And so you say, well, that's great. We just put them in orbit and just measure how the orbital planes precess. The trouble is there's a Newtonian effect. The Earth's quadrupole moment also causes a precession of orbital planes. This, in fact, is used to control certain satellite orientations. But it depends on the inclination. It's huge. It's 126 degrees per year. It's enormous. But for an orbit inclined in this direction, it moves that way. For an orbit inclined this way, it's a retrograde orbit, it's in the opposite direction. So all things being equal, if you took the two measured precessions of the orbits and added them, you would cancel out the Newtonian effect and be able to see the residual frame dragging effect. Well, life was a little more complicated than that. At the end of the day, one had to make use of data on all the multiple moments of the Earth from a mission called GRACE that has measured these moments with very accurate, very high precision. But combining the data from these two satellites plus data from GRACE that told us a lot about the multiple moments of the Earth, Ciuffolini and his colleagues reported a 10% measurement of the frame dragging. And then in 2012, there was a third satellite was launched called LARES. And so the idea is with these three satellites plus improving GRACE data, they hope ultimately to reach about a 1% measurement of the dragging of inertial frames. Okay. Okay. So that is there any, this sort of completes my discussion of weak field. I'm just going to spend 10 minutes beginning to talk about strong field tests, but are there any questions about what I've said so far about solar system experiments? Not yet. One of the problems is in order to have this nice cancellation of what I didn't mention was this nice cancellation works if the inclination of this one is supplementary to the inclination of this. In other words, if the sum of the two inclinations, that plus that equals 180 degrees. Turns out the Newtonian effects are equal and opposite for all multiple moments, which that would be terrific because you could really cancel. Before LAGEOS 2 was launched, relativists lobbied hard with NASA to get this thing launched into the supplementary inclination so that this cancellation would work. But this is a geophysics experiment, and the geophysicists wanted an inclination that would cover more laser ranging stations and they had their own criteria. At the end of the day, I mean, relativity is a small community. Geophysics is a huge community. They won the lobbying. So this was launched with the wrong, from our point of view, inclination. So this cancellation wasn't good enough, and that's why you needed this data to really get all the multiple moments measured independently. LARES, with huge lobbying from Ciuffolini, LARES was launched by the Italian Space Agency specifically as a relativity mission. Its name is Laser Relativity Experiment, something or other. So it was launched in the right inclination, but there was an error in the launch booster, and its semi-major axis is not what it was supposed to be. So you don't get the cancellation anyway because of a failure in some of the second booster or something. So again, they're still going to have to rely on independent measurements of all the multiple moments of the Earth. But again, 3 satellites plus all these improved measurements, they still think they'll reach 1%. And I think that's also why there's no results yet. I think it's because of this failure to get the right semi-major axis, it's going to be a very complicated analysis. Yeah, there's a follow-up GRACE mission. In fact, the plan is to use a GRACE mission with laser ranging using LISA technology, which is a nice byproduct of LISA. The current GRACE there are 2 satellites ranged with a microwave link, and you measure the distance between the satellites, and that's a way to measure the multiple moments. The next generation GRACE will have laser ranging, which will be much more accurate. All right. Okay, so in the last few minutes, I'm just going to have time to really talk about what I mean by weak field versus strong field gravity, and then next time we'll get into specifics. What you mean by weak field gravity depends on what kind of a physicist you are. And I don't mean a good or a bad physicist, but to a relativist, weak versus strong means the relationship between really whether the gravitational potential, Gm over r, is small or big, or whether the scale of your phenomenon is large compared to the Schwarzschild radius of, say, some body, or comparable to that. And so what I've put on this plot over a range of 60 orders of magnitude in distance, from 10 to the minus 30 to 10 to the 30 centimeters, and another 90 orders of magnitude in mass range. What I've done is plotted the curve where Gm over r is 1. So that would be the dividing line between strong and weak. So weak gravity, from a relativist point of view, are phenomena that occur on distance scales that are large compared to that m. So, for example, a hydrogen atom, a strand of DNA, human size, even the best accelerators are in a weak gravity regime. A measurement of G in the laboratory, given laboratory scales, laboratory masses, sits out here well in the weak field regime. A GPS orbit around the Earth sits about here. So relativistic corrections are important for GPS. The closer you get to this line, the more important GR is. Neutron stars here, the sun is here, the Milky Way is about there. And of course, black holes lie along this line, right? A stellar black hole, a supermassive black hole. Even the universe itself, roughly speaking, lies along this line, the present universe at end of inflation, simply because, roughly speaking, the mass inside our own horizon is roughly equal to that distance in geometrized units within a factor of 5 or so. So even the universe is on the edge of the strong gravity regime. There may be phenomena in here, but we don't care about them because they're inside the event horizon, so we'll never find out what they are. So from a relativist point of view, weak gravity sits out here, sun, GPS, Earth. Strong gravity are phenomena that are occurring the closer and closer you get to the line. Neutron stars, black holes are the exciting places for strong gravity. But if you're a particle physicist, you think of strong gravity rather differently. You really think about whether or not the curvature of space-time, or the radius of curvature of space-time squared, is larger than or smaller than your favorite length scale. Okay? So for a particle physicist, weak gravity are phenomena that occur when the radius of curvature is very large compared to your favorite scale. Strong gravity is when the curvature is so strong that it's comparable to or smaller than your favorite scale. So for a particle physicist, the dividing line between weak and strong, if L is the Planck scale, is this line here. And in a way, this tells you why it's so hard to find strong gravity effects from the particle physics point of view, because here they're not accessible to any experiment, and the only place where they do something that's that's observable is in the universe at the quantum gravity scale, right? Which is at the Planck scale. That's where you expect strong gravity from this point of view to occur if L is the Planck scale. So it's a kind of limited regime where you can actually think about phenomena involving strong gravity from this point of view. But that's true if it's the Planck scale. But perhaps L is not that, but at the TeV scale. Maybe that's the dividing line between weak and strong gravity from the particle perspective. So that gives at least some regime, say the universe at the end of inflation, where there might be interesting phenomena in this regime called strong gravity. And of course, the length scale could even be the Hubble scale, in which case sort of most phenomena would lie in the strong gravity regime if L were the Hubble scale. So it depends really on what you view as your fundamental scale from a particle physics perspective as to what's weak or strong. But I'm a relativist, so I'm going to adopt the relativist definition. Strong gravity means phenomena that are getting close to this line representing the black hole event horizon. So really we want to think about neutron stars and black holes themselves, and maybe to some extent cosmology as the strong gravity regime for testing Einstein's theory. So next time on Monday, I will begin a discussion of the first, historically the first example of strong gravity tests of general relativity, namely involving binary pulsars. So we'll talk about the various interesting binary pulsars that have been detected, and then we'll turn our attention to the dynamical regime of testing GR with gravitational waves. Okay? Any questions? Okay. Okay, no questions. Thank you.